Hi, today I'll talk to you about some work on the production of primordial black holes during inflation in the presence of spectator fields. And this is based on previous work with my collaborators, Sarah Geller, Dave Kaiser, Evan McDonough, and two undergraduate students, Zach Ireland and Kyle Widmeyer, plus some ongoing work with other collaborators. And this is motivated by two different points. On one hand, we know that in single field inflation, it is possible to produce primordial black holes with the mechanism of Ulta's law, and I will review this in a moment. On the other hand, there are good reasons to believe there could be multiple scalar fields present in the early universe, so it would be worthwhile to consider their dynamics. And so our question is, what happens if additional fields spectate the inflaton during these PBH producing single field models of inflation? And let's just jump straight into it. Inflation, you probably all know this, is this early brief phase of exponential expansion of space that was introduced in the 1980s as a solution to some outstanding problems of the hot Big Bang, notably the horizon problem, or why the CMB has the same temperature on opposite sides of the sky. And it is extremely well tested against real data. Now, in its simplest form, inflation is driven by one simple scalar field that lives in a certain potential. As it rolls down the potential energy causes the expansion of space. And because of Heisenberg's uncertainty principle, there will be quantum fluctuations that will eventually go into energy or density fluctuations. And after inflation, the inflaton transfers its energy into the standard model particles, creating the particles we know and love. And the main observable inflation is its curvature power spectrum, which we will see later, which is the two-point function of these quantum fluctuations and lives independent of the CNB. Now it is important because we know it is near scale invariant to approximately 8 sigma nowadays. On the other hand, what are primordial black holes? They form through the gravitational collapse over densities, unlike their younger stellar cousins, which could be sourced by inflationary fluctuations. So when these fluctuations that I mentioned earlier are large, they could collapse gravitationally and form these black holes. However, for this to be happen, they need a large enhancement of the curvature power spectrum above a threshold of 10 to the minus 3, considering that at CMB scales, the power spectrum has a value of 10 to the minus 9. And okay, sure, but why are they important or why are they interesting? Well, PBH are an interesting candidate for dark matter, a non-particle directly candidate for dark matter. And when I say this, I am going to focus in particular on the asteroid mass range for PBH as dark matter candidates. And they are also interesting for other reasons. For example, they could form the seeds for the supermassive black holes we see at the center of our galaxies, but this is beyond the scope of this talk. Now, I mentioned we need this large enhancement, but how can this happen? Well, in single field inflation, we can do this through the mechanism of Ulta's law. So the background dynamics of the inflaton are governed by these two equations: the equation of motion, where dots represent time derivatives, and the Friedmann equation on the right of the screen, where h is the Hubble parameter that describes the expansion of the rate of expansion of the universe, and v is the potential in which the inflaton lives. We define these two parameters: lower parameter epsilon, which defines the rate of change of epsilon, or the change of expansion of the universe, and eta, or the rate of change of the parameter epsilon. Note that this might be a different definition to what you're used to. Now, in the slow roll regime, which is defined as these two quantities being very small, the inflaton rolls slowly down its potential and allows for inflation to take place and to take place for sufficiently long as to match the CMB. There is another regime, the ultra-slow roll, which, as the name suggests, means the field rolls ultra slowly along its potential, which takes place when epsilon is near 0 and while eta is larger than this value of 3 in this definition. And this corresponds to the right-hand side of our equation of motion being approximately 0. And this will be important in a minute. Now, when this takes place, let's look at the perturbations. Well, the gauge invariant curvature perturbations follow this equation of motion. And in the USR regime, the middle term, the Hubble damping term, becomes negative. What this means is that for long wavelength modes, where the k over a is very small, these modes will go quasi-exponentially. And let's look what that means for a power spectrum. In a potential with that derivative of the potential being approximately zero, which, as we saw in the equation of motion, means that we have a USR regime. And this can be done by having a potential with a certain feature, a local bump, for example, in its inflationary potential, like the one shown here, which we will look at throughout this work. In this case, when the inflaton will arrive to that feature where d phi v is approximately zero, we will see that the modes go exponentially and we will get this enhancement of the curvature power spectrum, which allows us to produce PBH. And just for completeness, during this time, this is where the inflaton causes that bump. Our value of eta does cause the value of 3, so we have USR, and in fact, our curvature perturbations go exponentially. But this was for single field. I mentioned spectators or multiple scalar fields. What does this mean? Well, let me start by asking, is the universe simple? We all know that the Lagrangian of the standard model fits very nicely on this mug by CERN. But if we were to expand every term, it would look something more like this, which still fits on a mug, but is a bit harder to read. But jokes aside, multiple scalar fields are very possibly present in the early universe because of different reasons. Like even the standard model Higgs field is actually a complex doublet, so it is composed of 4 scalar fields. Now, obviously there's symmetry reasons in this case, but it is multiple scalar fields. And if we go beyond the standard model, we can have multiple Higgs. In the Axiverse, there's a prediction of having hundreds, if not thousands, of axion fields, which are scalar fields. And I'll come back to this very briefly later. And if we take string theory compactifications, for example, we could have several moduli fields. So I think it is worthwhile to consider the effects that these could have. And this has been done in the literature very extensively. So let me briefly review the multi-field formalism. And in this case, what this means is that there are multiple fields that contribute to the dynamics of inflation. So when this happens, if we have 2 fields, our inflaton phi and another field chi, there will be a fictitious or abstract field space. And our field system will evolve along this, on a trajectory in this field space. Now, unlike single field inflation, in this case, we will have quantum perturbations both along the trajectory of motion in this field space, which is also the case in single field, but also perpendicularly to this direction. And these are the curvature or adiabatic and isocurvature or entropy perturbations. The former is also present in single field inflation and affects the total energy density of the system, while the second does not affect the total energy density, but the ratio of particle species. Now, in this kind of setups, there can be turns in the trajectory of the field system in field space, such as the one diagrammatically represented here. When this happens, it is important to consider this quantity, the turn rate, which decides how the field may turn. Now, I mentioned we are considering a spectator field. This is the simplest case where we have the setup shown here. And for simplicity, we'll take the spectator potential to just be a quadratic term. Now, what it means by spectator field is chi does not have any direct coupling to the inflaton. It has a subdominant contribution to the energy density of the universe at all times, and a mass that is very small as compared to Hubble, so it's low volts. Now, from this setup, we see that there will actually be 2 equations of motion for the 2 fields, which are decoupled, not directly coupled, while the Friedmann equation will have these additional contributions due to the spectator and will therefore be increased. Another important thing in this case is that the slope parameter epsilon becomes sum separable with these 2 components here. Now, this thing gives us 2 effects, which are shown. The first one here, the fact that when the Hubble parameter is increased, the Hubble friction will be increased. And therefore, the inflaton will spend longer in the around the feature of this potential, which is shown here on the left. From the gray to the blue line, the inflaton spends longer in that phase 2 as I demarcate here, which is where it causes the feature. Now, the second effect is because epsilon is sum separable and because chi is slowly rolling at a certain scale, well, epsilon can actually set a floor to, epsilon chi can actually set a floor to the overall value that those lower parameter epsilon can have. So epsilon never becomes small, but we said that epsilon has to be very small in order for Ulta's law to take place. So does it? Indeed, if we plot the second law parameter eta, we see that while in single field in gray, eta does causes 3, it never does so in this spectator scenario. So USR is avoided. But what does this mean for PBH production? We know that the peak has to cost a certain threshold, but if we take this global approximation, note that this is an approximation in the case where the spectator is present, well, indeed, we wouldn't be producing PBH, but hope is not lost. Since we do have a spectator field or a second field, this becomes intrinsically multi-field. So in the our potential becomes two-dimensional. And if you look at the trajectory of our system along this potential, well, we see that it evolves along phi, then will briefly turn and evolve along the chi direction to then go on along its merry way along phi. And in this region, we see two turns in field space, and we see that the direction of the curvature and isocurvature modes swap. Now, this is important. First of all, the turns happen just around this phase that I was showing earlier, where epsilon has a floor and are opposite, and it actually sources a new mechanism. So to understand this, let's look at the equation of motion for the perturbations on super Hubble scales, which are given here. Now, omega is the turn rate we saw before, and in the second equation, mu s is an effective mass for the isocurvature modes that is given by background quantities, and is shown here. Now, what do these equations tell us? Well, the second one tells us that there will be a growth of the isocurvature perturbations whenever mu s squared is negative, so when it is tachyonic, which indeed we see is the case here. And the first one tells us there will be a transfer of power from the isocurvature to the curvature modes in the presence of turns in field space, which we saw do exist. And indeed, if we look at the evolution of the curvature and isocurvature mode, we see exactly that. A growth of S and then a transfer from S to R at a later time. And as a quick disclaimer, this mechanism of turns and tachyonic instabilities is not new. It has been studied in literature, but it has always required couplings in other kinetic or potential terms of your set. But what this means for us is that PBH production is safe. So from the single field case, when we had the spectator, we naively thought it would kill PBH production. But if we compute everything carefully, we see that not only is it not killed, but it can even be enhanced, as we see in the red curve in this plot. Now, a couple more things before I leave you. I just wanted to mention the generality of the mechanism, because so far I only considered one particular PBH model. Well, the direction of the field trajectory in field space is given by this unit vector. And so whenever epsilon chi becomes transiently larger than epsilon phi, as we saw is the case, we will see that there will be a change in the direction of this unit vector and therefore turns. On the other hand, during this phase 2 or would-be USR, the the isocurvature mass always becomes tachyonic because it is given by this form. The last term is approximately 0, the second is always negative, and the first one has to become negative at least at some point during that phase because the inflaton reaches a local feature, a local minimum or maximum reflection point, and then has to leave it. So because of this, the mechanism is generic to the family of model that produce PBH through a phase of Ulta's law. And another important thing is fine-tuning. So you might know that the PBH models are extremely fine-tuned. So before I get to that, let me just mention that in the spectator sector, there is a degeneracy between the initial condition of the spectator and its mass. So that if we change one, this enhancement of the power spectrum can be compensated by varying value parameter. But more interestingly, if we look at fine-tuning, well, in the single field case, a very small change in one of the model parameters, such as the parameter phi d here, small as in 1 part in 10 to the 4, could drastically change the observables. We quickly fall below the threshold for PBH production with this small change. Now, when we add the spectator, we can reproduce the same results, the yellow curve here, but with order 1 variation in our spectator parameters, we can reproduce the initial power spectrum and therefore have PBH production. So this gives us a reason to believe there is a resilience to fine-tuning added by the introduction of these physically motivated additional parameters. And one last thing I wanted to mention is, I mentioned the activerse earlier. Well, what if the spectator was not a quadratic potential, but actually an axion given by this sort of potential? And this is all preliminary work, but our first results seem to show that indeed the same scenario does happen. So you can see this floor set by epsilon, by chi, sorry, on the right-hand side. And this will indeed produce an enhancement of the curvature power spectrum, the red line, with respect to the single field case in blue. And therefore, this gives us reason to work on this, which is indeed something we're doing. And another interesting thing is that if we had two axion fields, again, the activerse predicts many of them, we can still have this sort of scenario where multiple axion fields contribute to the enhancement of the curvature power spectrum. And one thing that is important to note is that here the decay constant of the axion is slightly Planckian. We're talking about 0.5, but that should satisfy the constraints. And this is work that we are actually currently doing, and I find it quite interesting. So to leave you on some recaps in conclusion, we know that in single field inflation, some potentials can produce primordial black holes through this mechanism of ultra-slow roll. However, these require significant fine-tuning. On the other hand, spectator fields are likely present in the very early universe during inflation, and thus it is important to consider their impact on the dynamics. When we do that, we see they stop ultra-slow roll, thus naively killing PBH production. But when we do the calculation properly, we see they also source these new mechanisms of turns and isocurvature instabilities or tachyonic instabilities, which enhance the curvature power spectrum and therefore save, if not enhance, PBH production. And lastly, these additional decays of freedom seem to alleviate this issue of fine-tuning of the single field model. As next steps, and these are quite important, the first one is that we have to quantify this idea of fine-tuning that I mentioned. And to do this, we are calculating the Bayesian evidence of the single field versus spectator models by running MCMC. This is working in progress with my colleagues Param Upadhyaya, Sarah Geller, Dave Kaiser, myself, and Evan McDonough. And we are also interested, as I briefly mentioned, in looking at axion spectators, which is some work in progress with Michele Ciccoli, myself, Evan McDonough, and Francisco Pedro. And as additional things we are interested in looking at are reheating considerations, loop corrections, which can be important in this sort of models, and extended phenomenology. For example, if the spectator were to drive a second phase of inflation after everything we've seen, this could shift the peak of the power spectrum to larger scales. And so the PBH might not be candidates for dark matter directly, but they might be seeds for supermassive black holes. So lots of interesting things to look at with this. And on this note, thank you very much for your attention. And I look forward to hearing and reading any questions you may have and discussing these topics in more depth during the conference. Thank you and goodbye.